Good morning, class. We're looking at college algebra practice test number 3, module 3, covering chapters 5 and 6. Here's chapter 5, polynomial and rational functions. Second part. So we have a function. Let f of x be x over x minus 2. We want to sketch the graph of f using technology to determine whether f is a one-to-one function. We have seen how to graph rational functions. This is going to use technology, so it's going to happen pretty fast. And yes, it is a one-to-one function because it clearly passes HLT, horizontal line test. Remember, a function is a function where it passes the vertical line test, meaning no x coordinates repeat. A one-to-one function passes a horizontal line test. That means the y coordinates can't repeat either. And you can see the vertical asymptote, the horizontal asymptote. The vertical asymptote, x equals 2 when the denominator is 0. Horizontal asymptote, the degree of the numerator and the denominator is 1. So the coefficient of the top is 1x. This is 1x, 1 over 1. So y equals 1. So you can see that. Now, if f is 1-to-1, and we said yes, it is, find f inverse and sketch the graph of f inverse, again using technology. And recall, if this is f of x, we just change the name to y to make it easy to work with. We interchange x and y. So this becomes x, this becomes y, this becomes y. That's the first step, interchanging x and y. Right here, we have the inverse. However, we solve for y. To solve for y, we do the cross product. We multiply these two, we multiply these two, and when we multiply these two, we get x times y minus 2x equals y. So since we want to solve for y, moving things around in the following manner. Everything involving y should come together. So this moves this way, becomes negative. This moves this way, becomes positive. As we move the y to the left, we factor the y out, we get y times x minus 1. Maybe I write that. So this becomes xy minus y equals 2x. On the left side, you take the y out, and now you are going to divide both sides by x minus 1. So y becomes 2x over x minus 1, or f inverse. Or f inverse. Using technology, we can graph. And when we look at the asymptotes, notice vertical asymptote for this one is x equals 2, which corresponds to horizontal asymptote y equals 2 for the inverse. Horizontal asymptote for the original function y equals 1 for the inverse corresponds to a vertical asymptote x equals 1. Now, we want to find the domain of the function f. If you go back to this function, you set the denominator equal to 0 and you exclude it. So x can't be 2. In other words, you write x minus 2 is 0, x is 2, and therefore a shorthand notation, x can't be 2. If x can't be 2, in interval format, you write negative infinity to 2, union 2 to infinity. Now, parentheses make sure that the 2 is not included. Now, for the rest of them, we're going to write this one first because domain of f becomes range of f inverse. We write the same thing for the range here. Now, domain of f inverse, this is f inverse. You set the denominator equal to 0, x becomes 1. And you exclude that x can't be 1 is the domain. How do you write x can't be 1? Negative infinity to 1, union 1 to infinity. Again, you use parentheses around the 1. And that's the same as range of f, which is minus infinity to 1, union 1 to infinity. That's how you do that. Solve the following inequality, graph the solution set, and write the solution in interval notation. Anytime you want to do that, you are going to use sign graph, okay? The sign graph makes life easy from negative to positive infinity, and to do so, we are going to factor everything. In other words, the bottom is fine, the numerator has to be factored. You want two numbers, the product is negative 18, the sum is negative 3. So I'm going to put those signs at top. So the product must be negative 18, and the sum must be negative 3, positive 3, negative 6. Now, what makes the numerator 0 is negative 3, positive 6. What makes the denominator 0 is negative 2. So those are the critical points, if you will. If you set this one equal to 0, x equals negative 3 and 6. If you set this one equal to 0, x equals negative 2. And these are the numbers that you put on a number line from smallest to largest. Okay. At negative, so x goes from negative to positive infinity. At negative 3 f of x, we're going to call this f of x, everybody. Let's call this expression to make it, or you have to write it, or you have to write the expression. At negative 3, it's 0. At positive 6, it's 0. At negative 2, it's UD, undefined. So what happens is that you pick TPs, short for test points. What we are going to do is called sign graph, everybody. So to the left of negative 3, for example, negative 4, between the two, negative 2.5. Between a negative and positive, the easiest point would be 0, and beyond 6 is 7. Now, one thing I want to make a point of, notice this one has degree 1, this one has degree 1, this one has degree 1. That means they have an odd degree. Therefore, if you find out what happens in one spot, the rest of them alternate. The easiest point would be 0. What happens when you put the 0 here? You have two choices. You can put it into here, which becomes negative over positive, because this goes away, right? Negative 18 over 2 positive. Negative 18 over positive 2 is negative 9, so it's negative. Or put it here. If you put 0, you get positive times negative over positive. This becomes negative. If this is negative, the rest alternate. So negative, this becomes positive. Negative, this becomes positive. Positive, this becomes negative. Or as I mentioned, plug in. So plug in, for example, if you plug in negative 4, just to give you an idea, it's easier to plug it in here. If I put negative 4 here, this becomes negative. Negative 4 here, this becomes negative. Negative 4 here, this becomes negative. Negative times negative divided by negative is negative. So remember, you don't have to evaluate the exact value for that. You just want to know whether it's positive or negative. So now, let me erase my work. Going back to this, we want it to be greater than or equal to 0. So anywhere that is positive is the answer. So in this vicinity and in this vicinity. From -3 to -2, union 6 to infinity. Now, is -3, because it has an equality, is -3 included? Yes, bracket. Is -2 included? No, because at -2, the denominator becomes 0 and it's undefined. Union 6 is included? Yes, because it becomes 0 to infinity. And by the way, infinity or negative infinity always is taken a parenthesis because it's a concept. And as far as the graph is concerned, you shade the region in between these two numbers and beyond number 6. So this is one way to do that. Now, notice -2 is not included, takes a hole. This one takes a solid point here and continue. Sometimes they use bracket, okay? And for the hole, they use parentheses. Now, what I want to add is this. What if, and I'm going to make it, let's say, part B, just for the sake of argument. If the question was asking for the following, you would use the same sign graph. The only change that you make is here, everybody. This changes to bracket because at -2, this becomes 0, not undefined, okay? Just to give you an idea. Now, if the sign changes to less than or equal, you use the same sign graph, you just answer accordingly. For example, if this was negative, you would use where it's negative as the answer. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. F of x equals a sub n x to the power of n all the way to a sub 0 look like y equals a sub n x to the power of n. So it looks like that. So what do we mean by that? Let me just do some work here. If the degree is even and the leading coefficient positive, remember this is the leading term. A sub n is the leading coefficient. So this is the leading term. A sub n is the leading coefficient. So what this says, if n is even, ultimately it looks like y or f of x equals either x squared or minus x squared. Depends on what? Depends on this number. If this number is positive, like y equals x squared, remember when a is positive, it opens up. If this number is negative, it looks like y equals minus x. Just remember that. So what does it mean? In this case, whether x goes to negative or positive infinity, f of x goes to positive infinity. In other words, the first and the second quadrant. For this one, whether x goes to negative or positive infinity, f of x goes down to negative infinity, which means the third and the fourth quadrant. What happens if you have the same situation, but the degree is odd? If the degree n, this number is odd, it either looks like y equals x cubed or y equals minus x cubed. If a sub n, if this number is positive, looks like y equals x cubed, which means the first and the third quadrant, okay? X goes to negative infinity, so does y. X goes to positive infinity, so does y. By f of x, we mean, remember, f of x is the same as y. But if a sub n, this number is negative, the leading coefficient, then it looks like y equals minus x cubed, the second and fourth quadrant. That is known as the end behavior. In other words, x goes to negative infinity, y goes to positive infinity, x goes to positive infinity, y goes down to negative infinity. This is known as the end behavior of the function. So that is extremely important to understand. And that will help us graph polynomial functions. Okay. Also, we have behavior near a zero, root, x-intercept. They all mean the same thing. First, let's discuss the multiplicity. 0, x minus c, we have a factor of x minus c to the power of m. M is called the multiplicity. That means how many times it repeats. If m is odd, f crosses the x-axis at c comma 0. If it's even, f doesn't cross, it has to bounce back. So look at this one, for example. It crosses, it can't cross, it crosses. In this case, simply put, polynomial functions with the multiplicity of 1, 2, 3. And when it's odd, it has to cross, but when it's even, it can't, it bounces back. The higher the multiplicity, the flatter the curve is at the 0. The sum of the multiplicities is the degree of the polynomial function. Number of zeros theory. A function defined by a polynomial degree n has at most n distinct or unique complex zeros. Now let's put all of this together to get to some graphs. We want to graph the following polynomial using the end behavior and behavior near an x-intercept. So let's see how we do that. First and foremost, it's a good practice to be able to write it in factored form, which means I can put these two together and take out x squared. And to make sure we have the same thing. If I take the x squared out from the first two, I get x squared times x minus. So right here, I get x squared times x minus 5. And I hope you realize to make this look like that, all you have to take a negative 1 out. So now it's the common factor of x minus 5 times x squared minus 1. This is basic factoring. And everybody knows x squared minus 1 follows a squared minus b squared. Which factors into a plus b, a minus b. Remember, 1 is the same as 1 squared, 1 cubed, you name it. So it becomes x plus 1, x minus 1. So now we have 3 x-intercepts, 5, 0, negative 1, 0, 1, 0, and all of them have, look at the exponent. No exponent, that means exponent 1, multiplicity 1. So x-intercepts, all with m. M stands for the multiplicity. all have the same multiplicity, namely 1. So we have 5, 0 here, negative 1, 0 here, 1, 0 here. So we're going to have those. So we have the end behavior. And because the multiplicity is odd, not just 1, it's an odd number. And that's what, whether it's 1 or 1001 makes no difference. Odd, that means it crosses. The graph crosses those. And let's see what else we can add to this. The y-intercept can be found. It's easier here. You can use any of them. 0, 0, 0 is 5. So the y-intercept is at 0, 5. So let's locate that. This is 6, so somewhere here, a little bit below number 6. And remember, if you look at this one, x cubed is the leading term. N is 3, which makes it odd, and a sub n is 1, which is positive. So the end behavior depends on the leading term. Which means the first and the third quadrant. As x goes to negative infinity, so does y or f of x. As x goes to positive infinity, so does y or f of x. So that means like so. And that's the graph, and that's a little bit more precise. All right, we are ready to move on. For a graph the following function, it is given to us in factored form. So first, easy part, we start with the x-intercepts. This one gives us 2, 0, and the multiplicity is 2. This one, if you set equal to 0, gives us negative 3 halves. 2x plus 3 equals 0. We get negative 3 halves. So negative 3 halves, 0. Multiplicity is 1. So we have these 2 points. This is negative 3 halves, 0. This is 2, 0. Now in calculus, we use a double arrow to show the multiplicity of even. It doesn't matter, it's 2 or 2,000. The fact is, when it hits that, it can't cross that. Now, I hope you recognize this. If you raise it to the power of 2, you get x squared times 2x, you get 2x cubed. And as far as the y-intercept is concerned, you replace the x with 0. So 0 gives you negative 2. Square it gives you positive 4. 0 gives you 3, right? Times positive 4, 12. So we have this point also. And now, as I mentioned, the end behavior You don't have to work everything out. You just want the first term. How do you know it's 2x cubed? This is x squared times 2x. X squared. Again, I can work it out just to show you an idea how it looks like. This part, as you know, it's x squared minus 4x plus 4. But if you multiply these two, you get 2x cubed. Why is this important? Well, this is the leading term. The end behavior follows the x cubed because the leading coefficient is positive. So n is 3, n is odd, and a sub n is positive. So the end behavior depends on 2x cubed, the leading term. Since n is odd, we are looking at the first and the third quadrant. N is odd, a sub n is positive. So as x goes to negative, so does y to negative infinity. As x goes to positive infinity, so does y or f of x. Looking like that, and this is a better looking graph, everybody. What is the least possible degree of this polynomial? Write an equation for the polynomial. So to do so, let's just go over a couple of items. Turning points, where the graph of a function changes from increasing to decreasing or vice versa. So this is decreasing, increasing, so that's one term. Increasing, decreasing, that's another one. Decreasing, increasing, that's another term. The number of turning points of the graph of a polynomial function of degree n, and n is larger than or equal to 1, is at most n minus 1, at most. Local maximum point, highest point or peak in an interval, function values at these points are called local maximum. So peak. Local, so that's a local max. Local minimum point, lowest point or valley in an interval, function values at these points are called local minimum. So this is a value, local minimum, this is a value local minimum. By the way, this happened to be an absolute minimum because no other point has a smaller y coordinate. Extrema is the plural of extremum, including all local maxima and local minima. So that was something we wanted to know. And so we want to know what is the least possible degree. So how many terms? One, peaks and valleys. When we say terms, peaks and valleys. 1, 2, 3. And remember, when the degree is n, at most n minus 1. So the reverse process, we have to add 1. So the degree must be 4. Why is that? Because we have 3 terms. We're going to write the equation. So to write the equation, we are going to use the given information. We are going to write the intercepts and use them. So what are the intercepts? I see this one, I see this one, and I see this one. This one at -3, this one at -2, This one is at +1. Multiplicity is odd because they cross in both cases here, but notice it bounces back. Multiplicity is even. So those are the three intercepts. Multiplicity is 1. And this one, we're going to go with the least amount. Multiplicity is 2. And we put the arrow again. That means it bounces. So notice it bounces back. So what would be the function? Well, this means x minus minus 3, meaning x plus 3. This is x minus minus 2. That means x plus 2. This means x minus 1, quantity squared. So f of x is the product of all of those and something else. We're going to say a. So f of x is something which we don't know the leading coefficient. X plus 3, so this is x plus 3, this is x plus 2, and this is x minus 1, and the reason we square it because multiplicity is 2. Now, the question is, how do you find a? Well, you pick the easiest point that you can read from the graph, any pair, and you can find the answer. For example, y-intercept is clearly located at 0, 3, which means replace the x with 0, and f of x or y with 3, you can find the missing a. So we say this is 3, and now we're going to replace the x with 0, so this becomes 3, this becomes 2, this becomes minus 1. Squared a remains. So let's see what we have. This is 1, 6a. A becomes 3 over 6, or 1/2. So f of x is 1/2 x plus 3. We go back to here, x plus 3, x plus 2, x minus 1 squared. That's the answer, everybody. So very straightforward. Hopefully everybody is okay with this. We are going to move on. Find the degree, leading coefficient, and the maximum number of real zeros of the polynomial f of x equals 2 plus 3 x to the power of 6 plus 4 x to the power of 7 minus 6x. Also describe the end behavior, which is also known as a long run behavior. To do so, first reminding everyone of what we had mentioned before. A polynomial function of degree n in variable x looks like that, a sub n, x to the power of n all the way to a sub 0, where each a sub I is real, a sub n can't be 0, and n is a whole number. Remember, whole number meaning 0, 1, 2 to infinity. A sub n is called the leading coefficient. A sub n x to the power of n is called the leading or dominating term. That might make more sense. A sub 0 is the constant. We're going to put this in descending order. So that means this comes first. This comes second, third, last. There are things missing in between, but anyways, this is the leading term for x to the power of 7. What is the degree? 7. What is the leading coefficient? 4. Maximum number of zeros has to be the exponent, the degree, 7. And behavior? Well, depends on this. N is 7, odd. A sub n is 4 positive, behaves like x cubed. So this is the leading term. N is 7, which makes it odd. A sub n is 4, which makes it positive. Behaves just like x cubed. Which means as x goes to negative infinity, so does y, meaning f of x goes to negative infinity. As x goes to positive infinity, so does y, meaning f of x goes to positive infinity. So pretty straightforward, everybody. Use number of zeros theorem and Descartes' rule of signs to discuss real zeros of f of x. Fill up the table, where f of x is given as 3x to the power of 7 minus 4x to the power of 4 plus 3x cubed plus 2x squared minus x minus 3. So notice the leading term is 3x to the power of 7. Because n is 7, the maximum number must be 7. So the total must be 7. If you go to this table, it's discussing the zeros. Total number of zeros can be 7. Now, what is Descartes' rule of sign? That's what we want to discuss. Descartes' rule of sign determine the number positive and negative zeros, the number of let f of x be the polynomial function as described. F of x is a sub n, x to the power of n, all the way to n sub 0. With terms in descending powers of x, and that's important, has to be in descending. A, the number of positive real zeros either equals the number of variation in sign occurring in the coefficient of p of x, or is less than the number of variation by a positive even integer. That means you find the numbers, and then you can subtract 2 and 2 and 2 and 2. That's the idea. Whereas the number of negative real zeros either equals the number of variation in sign occurring in the coefficient of p of minus x, or is less than the number of variation by a positive even integer. So what do we mean by that? That's what I want to go over. Well, let's look at this one. So the first part, the number of positive real zeros either equals the number of variation in signs occurring in the coefficient of p of x. So let's look at this one. Never mind subtract. So if you look at the coefficient, this is positive 3. This is negative 4. 4 is not important, it's negative. This is positive, this is positive. So let's just write those. Just write the signs. Just the signs. Again, the number of positive real zeros either equals to the number of variations. So what variation do we notice? This varies from positive to negative, negative to positive, but there's no change here. There's a change here, positive to negative. There's no change here. That's what they mean. So take a look. This changes, we have 1. This changes, we have 2. This doesn't change, nothing. This changes, we have 1 more. So we have 1, 2, 3 changes. Again, positive to negative, negative to positive. Positive to positive, there is no change. Positive to negative, there is a change. So it gives us number 3. And then negative to negative, there is no change, everybody. So we have positive real zeros number 3 here. Now, the positive real zeros, just to give you an idea of what they mean, or is less than the number of variation by a positive even integer. Then you subtract an even integer. The first even integer is 2. So subtract 2, you get 1. And then you can't go negative. Let's say this was 12. Then you would go 10, 8, 6. You could keep on subtracting 2. You could do that. In this case, if I subtract 2, I get to 1. Then if I subtract another 2, becomes negative. And I can't do that. So the next one would be 1. But let's look at this part, the number of negative real zeros. Let's evaluate f of minus x. It says p of minus x, f of minus x here. So if I replace the x with negative, this becomes f of minus x. So let's do that. What is f of minus x? This becomes any of them that has an odd exponent changes the sign, even doesn't. So this has an odd exponent, becomes minus 3x to the power of 7. This doesn't change because the exponent is even, right? Minus x to the power of 4 is the same thing. This one has exponent odd, becomes changes sign, minus. This doesn't change sign, remains. This has exponent 1, it changes, and this is a constant, doesn't change. So this becomes negative. This doesn't change. This becomes negative. This doesn't change. This becomes positive. This doesn't change. So let's look at the signs according to this. Negative to negative to negative, nothing is changing. But negative to positive, there is a change. So first, let's write all those signs. So this, there is a change. This one, there's no change because positive goes to positive, and this one also there is a change because positive changes to negative, and that's important to understand. And so there is one change here, one change here is 2. So negative real zeros would be 2. This is the Descartes' rule of sign. Let me explain that one more time so everybody understands what's going on. First, you look at the original one and just make a note of the signs. As the sign changes, just look at how many changes. Positive to negative or negative to positive is considered one. So one here, one here, one here, total of three. Then you look at f of minus x, and that gives you, again, you look at just the sign, negative, 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 no changes. Here there is one, here's another one, total of two. So you have three positive zeros because there are three changes for f of x. You have two because of the negative gives you two. But the total is supposed to be seven. How do you get to seven? What is missing? Two more, because 3 plus 2 plus what number is 7? 2. What would that be? Imaginary zeros. So if it's not positive real or negative real, it has to be imaginary. That means this means a plus bi, everybody. Now, it's important for everybody to know imaginary must happen in pairs, because if a plus bi is a solution, so is a minus bi. So if they happen in pairs. So if this is not even, it's wrong. I want you to know that. What else can we do? We can take this down by 2 and it becomes 1. If I take this one by 2, it becomes 0, then we have 6 here. Or you can take this one by 2 becomes 1. This one you don't take it. If it's 2, then this becomes 4. So there are other ways of writing it. Or you keep the 3, this goes down. Okay, and again it's 4. Those are possible solutions, real zeros and imaginary.